Hi guys, this is going to be a video on isomers. As you're drawing molecules, inevitably you're going to come up with very complicated structures oftentimes, right? And isomers are generally going to pop up the more complicated your chemical formulas get. And so what is an isomer? An isomer is any chemical compound which has the same chemical formula, but it has a different structure. For example, if we took the compound C3H6, right? C3H6. Well, we can go through the Evo chart and try and figure out, hey, um, how many covalent bonds there are, how many non-bonds there are. And so if we do that, elements, valence electrons, octet, right? There are 3 carbons, 6 hydrogens. Each carbon has 4 valence electrons, 4 octet electrons, right? Look in the periodic table for that. Hydrogens, there's 1 and only 1 is needed in the octet, right? So in total, that's 3 times 4 plus 6. That'll be 18. Once you do the math, 3 times 4 plus 6, or 18, right? So there are 18 bonding electrons, and so that means there are 9 covalent bonds and 0 non-bonding electrons, right? That's 18 minus 18, or 0 non-bonding electrons. So, 9 covalent bonds, well, you have all of these atoms all over the place, so you got to figure out, well, where do these covalent bonds go? Okay, where do these covalent bonds go? One trick for these kinds of compounds, right? Hydrogen is special in that it only tries to make one covalent bond, right? Hydrogen is special in that it only tries to make one covalent bond. So you know that 6 of these covalent bonds, right? In total, 6 of these covalent bonds are from hydrogen. And so that means if we subtract off those 6, right, there's going to be 3 covalent bonds between the carbons. Okay? Right? 9 total covalent bonds, 6 of them have to go to hydrogen. So that means there are 3 covalent bonds distributed between the carbons. And so you might be scratching your head, all right, well, let's try to connect those carbon atoms together. We have 3 of them, right? We have 3 of them. Well, one way we could connect it is like this, right? That's 1, 2, and then, well, we'll have to put a double bond somewhere. So I'll put it there. Okay. And then if we were to then draw the hydrogens in, so each carbon should have 4 covalent bonds coming out of it. In general, the number of octet electrons is going to be the number of bonds an element makes. This carbon only needs 1 more bond coming out of it. 1, 2, 3, 4. This carbon needs 3 coming out of it. So 1, 2, 3. And indeed, that accounts for all 6 of our hydrogens. And so we know that this is one correct structure. However, if you notice, there's also another way that we can draw this. We can connect the carbons, but instead of putting a double bond here or here, we can actually connect the first and third carbons. This is what's known as a ring. Okay? And so looking at this, and then completing the structure, so each carbon gets 2 hydrogens, and you can verify that each carbon has 4 covalent bonds around it, so it has the octet. What you'll notice is that this carbon here in the first structure is connected to 2 hydrogens. This carbon here is connected to 1 hydrogen, and this carbon here is connected to 3 hydrogens. Meanwhile, in this second structure here, each carbon is connected to 2 hydrogens. So we know that they indeed have a different structure because they have a different arrangement in their bonds, right? So these are 2 isomers of C3H6, all right, of C3H6. One way we can tell almost definitively whether there is an isomer is by calculating the degrees of unsaturation for a molecule. Okay, degrees of unsaturation, well, what is that? It's going to be given by a formula that's given to you, sorry. So the symbol for degrees of unsaturation is the Greek letter omega, and it serves as a way for you to quickly tell how many double bonds, triple bonds, or rings are in a structure. And the way we calculate it is pretty straightforward. Lot, so there's just a lot of terms, right? 2 times the number of carbons plus 1, plus the number of group 15 elements, minus the number of hydrogens, minus the number of group 17 elements, and we divide that entire thing by 2. Okay? So if we took a look at our previous molecule, C3H6, and we tried to calculate the degrees of unsaturation, well, the degrees of unsaturation for C3H6 is going to be equal to 2 times the number of carbons, so 3 plus 1, plus the number of nitrogens, that's 0, minus the number of hydrogens, that's 6, minus the number of halogens, that would be X groups. There are no halogens, so no fluorines, chlorines, bromines, or iodines. So that's 0 there. And if we then divide this entire thing by 2, we'll simplify. 2 times 3 plus 1, 3 plus 1 is 4, so 2 times 4 is 8. 0 and 0 don't matter, but we do have a minus 6. So that's 8 minus 6, or 2. 2 divided by 2 is 1. Okay, so our degrees of unsaturation for this molecule is 1. So 1 degree of unsaturation, right? A double bond counts as 1 degree of unsaturation. A triple bond counts as 2 degrees of unsaturation. And a ring counts as 1 degree of unsaturation. So, right, we can look at this degree of unsaturation and know immediately, hey, there's probably a double bond or a ring. Okay, there's probably a double bond or a ring. And so, indeed, if you try to draw just the carbons between them, well, there's probably a double bond somewhere. You can't put a double bond on a hydrogen because that would exceed its 2 electrons, so it has to go between the carbons, right? So one way you can do this is by, of course, just connecting the carbons. Okay, just connecting the carbons. And then you know that there just has to be at least, or exactly, 1 double bond somewhere. Okay? Or the other option is putting it inside of a ring. Okay? So these will be the carbon skeletons for our isomer. All right? And then the same as before, you just put the hydrogens there and everything will be good. All right? Hope that helps. Take care.